Okay, well, let's start. We're like 3 minutes after the hour. So everyone, welcome to Compass. And it is a wonderful treat today to introduce our speaker, David Painemal. He is currently a senior lead research scientist of the satellite cloud group at NASA Langley, where he's also the supervisor of the group. He's been there about 10 years. David went there as on a postdoctoral fellowship after graduating from Erasmus about 10 years ago, in 2011, and has been there since. So very proud of his achievements, which include getting the Lawrence Award for Outstanding Publication in 2016. So now we will be treated to hearing about David's endeavors, ongoing endeavors as part of this group.
Thanks, Vakita, for the kind introduction. And can you see my, let's see, I'm sharing now, and I'm going to see, does everything look okay?
Looks good.
Okay. So thanks again, Paquita, for the kind introduction. So this is this presentation is it's several things together. And on the one hand, it's a summary of part of my research during the past 3-4 years. But at the same time, I'm going to show it's a little advertisement for the type of products that we are producing in NASA Langley. It's also a little bit of a review on the topic of aerosol-cloud-radiation interaction. And lastly, and perhaps equally important, perhaps it could be used as a motivation or introductory class for a remote sensing course on aerosol cloud remote sensing. So what I'm going to show here is a perspective from a satellite point of view, which is not perfect. Has a lot of issues, but has the very powerful advantage that you can see the entire, almost entirely the entire planet, and we can do some nice research and assessment combining a number of satellite sensors. So I will start with a very, very simple introduction on the problem. So we know that we need aerosol for cloud formation, and for a number of thermodynamical reasons, creating a cloud is easier when you have an aerosol compared to not having anything at all. So we know we need aerosol, atmospheric aerosol in the atmosphere. And one could think about what could happen if we perturb the atmosphere by adding more aerosol, which is a question that Sean Toomey in 1977 and tried to answer what would have happened, or what is happening now compared to 102 years ago with in terms of cloud properties due to an increase of on the aerosol loading. So he, using some theoretical considerations and observations, he showed that by modifying the aerosol, by increasing the concentration of aerosol, the albedo or reflectivity of the cloud could be also altered in a dramatic way, which is shown in these simple figures here. So let's think for a moment that we are in a clean environment and with a given number of atmospheric aerosol, and with a certain population of droplets with a specific size and concentration. Then we perturb the environment, and we are going to call it more polluted environment. We have more aerosol, and then we see some interesting changes in cloud microphysics. Namely, the droplets become smaller, and at the same time the concentration goes up. So we have more droplets, but they are smaller. So assuming no changes in the meteorological conditions and the macro structure of the cloud, these two changes in size of the droplets and the concentration drives an enhancement of reflectivity of the cloud and what it reflects back to space. And this is certainly an oversimplification of the problem. There are many other aspects that need to be taken into account, a number of feedbacks that currently researchers are looking into. But for the sake of this presentation, I'm going to start with this very basic argument, which is changes in aerosol concentration might change the relative properties of the cloud through changes in the cloud microphysics. So then the question that the research community is trying to answer is what has happened during the past 200 or 300 years in terms of the cloud interaction with aerosol, especially considering the changes in aerosol from pre-industrial time. This is simple but nice figures from Nicolas Belouin paper, his review paper 2020, and this shows the pre-industrial condition as we imagine they were in 1750. Of course, the population number of humans in the planet was much less than now. There were some natural sources of aerosol, namely biomass burning, biogeochemical processes, etc. And then we move to present day conditions in which we have desertification, less trees, possibly more biomass burning events everywhere in the planet, pollution, ships, and airplanes, etc. So we have a highly perturbed environment due to increase of aerosol, and many types of aerosol, and most of them caused by human activity, directly or indirectly. So what the research community is trying to do is trying to come up with numbers for these changes, and which is very challenging because we don't know exactly what the pre-industrial conditions look like. But having said that, a fascinating aspect about this interaction between aerosol and cloud and radiation is that we can see these changes in a number of processes. And we can actually see it in real time, which is showing here. And the visible image here from MODIS sensor shows a number of lines that resemble clouds that exactly match the ship tracks, which is what we call the ship tracks. So what's happening here is that the aerosol perturbation associated with ship tracks is causing changes in the properties of the clouds, and eventually this yield an enhancement of the albedo of the cloud. This is also shown in this satellite products here, which is a droplet size of the cloud, and it shows these lines or these ship tracks with droplets that are much smaller than the droplet size you will observe in clouds that have not been perturbed, especially over this region. So you have droplets of around 6 micron, but when you move away from the ship tracks, the droplets increases up to 16 or even 20 microns. So we have clear evidence that these things are happening now. But the challenge is trying to address the problem as a whole. And this is, I really need to apologize for showing this figure because I'm sure many of us are very familiar, and we show this figure again and again because it's really a nice motivation for continue doing research, right, and writing proposals, why it matters, this aerosol-cloud-radiation interaction. So this is a radiative forcing of climate from the IPCC report of 2013, the 5th assessment, and it shows the forcing and the radiative forcing for a number of anthropogenic agents. We know that the greenhouses produce a warming effect, and we're highly confident about this effect. But then if we move down, we find the aerosol radiation interaction and aerosol cloud radiation interaction first, and it's a negative forcing, that is a cooling. And our uncertainty is quite large, which is represented by error bar. So the uncertainty, especially for the aerosol cloud interaction, is around 1 watts per square meter, which is almost more than half of the entire total anthropogenic forcing. So we have a wide uncertainty in the anthropogenic forcing due to the aerosol cloud and radiation interaction. So I just wanted to show a little update from the Belouin paper 2020. What they concluded was that the forcing of the aerosol radiation cloud interaction is approximately, it is very similar to the 5th assessment of the IPCC, but it's slightly more negative. And the uncertainty is even a little bit larger. So during the past 5 or 7 years has been some progress, but in terms of the magnitude of the forcing, our ability to try to reduce this forcing hasn't been that successful. So how do we approach this the problem of quantifying the aerosol indirect effect using satellites? And there are a number of satellites orbiting Earth, but perhaps the most interesting constellation from a cloud aerosol interaction point of view is the so-called A-Train or afternoon constellation, which is a constellation of satellites with the same orbital track. That means that they are very close to each other in time. And many of the satellites have very important key sensors for sampling aerosol and clouds. We have CloudSat, which is critical for sampling precipitation and vertical structure of clouds. Then Calypso, which is particularly critical for the aerosol component, the 3D structure of the aerosol. And we also have Aqua that has a number of satellite sensors that I will be talking a little bit more about in the next slides. So one of those sensors is Ceres, which is one of our flagship sensors. Is aboard multiple satellites, Terra, Aqua, SOM MPP, NOAA 20, and it's a very well calibrated sensor that it was designed thinking in the climate data record. So the idea of the project was having a long term of very reliable measurements that will help us understand the flow of energy at the top of the atmosphere and visible and infrared. So as I'm sure many of you know, these measurements are really critical for understanding the planet's energy budget and the energy imbalance, which is really the physical foundation for climate change. And the second sensor is Calliope or Calliope. I'm going to say Calliope. And it's on Calypso satellite, and it's a LiDAR and at 2 different wavelengths. And this sensor is really critical for resolving the vertical structure of aerosol and vertical structure of some clouds, as long as the clouds are thin enough to be penetrated by the laser. And it's not really secret that Calypso has dramatically changed our view of aerosol in a 3-dimensional sense. So what can we derive from satellites? What type of cloud properties we can derive from satellites? So we can derive some basic properties such as cloud phase, whether the cloud is liquid, super cool, or ice, and temperature of the cloud, and height of the cloud, pressure of the cloud, and microphysical properties includes cloud optical depth, and which is the ability of cloud to extinguish light. So cloud optical depth in a way is correlated with the physical thickness of the cloud, but it has more sense from a radiative point of view. And droplet effective radius, which is a statistical measure of the size of the droplet, of a population of droplets. So I'm using here the standard method, the standard series algorithm derived by Minis et al. In 2011, 2020. And here I'm showing an example of 2 products, cloud droplet effective radius on the left and liquid water path on the right. So what I want to emphasize here is that by combining different swaths and different orbits of the satellite, we can put together a collage that allow us to observe almost entirely the planet. Same thing for liquid water path. And there are some clear spatial patterns here that I will be discussing in a couple of slides more. And now Calliope aerosol properties. We can have information about the aerosol type we're having, and whether it's dust, smoke, polluted continental, marine, or polluted dust, etc. And we get vertically resolved information of the aerosol, namely aerosol extinction coefficient, and other properties that can be used for characterizing the optical properties of the aerosol. And this is a nice slide put together by some people at NASA Langley, and it shows the way it works. And so basically the LiDAR observe curtains of profiles, really. And you see here the aerosol in the boundary layer, and you see also some other features that corresponds to clouds. So let's talk briefly about the radiative and cloud microphysical properties of clouds. So this is a series climatology of net cloud radiative forcing. In other words, it shows the importance of cloud from a radiative point of view relative to clear sky conditions. So in blue and magenta indicate the cooling effects of clouds, and orange and red is warming. And we can clearly identify a number of regions over the ocean where clouds are dominant in terms of cooling. And again, it's not a surprise for many of us that these are boundary layer clouds, are clouds below 2 or 2.5 kilometers that are mostly located in the subtropics, the Eastern Pacific, the Southeast Atlantic, and also part of the Southern Ocean, and also the mid and high latitude in the Northern Hemisphere. So cloud radiative cooling regions and cloud radiative cooling is dominated by regions with low clouds. So now we take a look at the cloud droplet number concentration. So this is not really direct retrieval, meaning that we have to estimate cloud droplet number concentration, making a number of assumptions about the cloud properties. And the main assumption is that we're assuming that the cloud is adiabatic. And so by combining these assumptions, and we can debate whether these assumptions are realistic or not. But by making these assumptions, we can derive a global climatology of number of droplets, cloud droplet number concentration, which is what I'm showing here. This is for low clouds below 3 kilometers. And you see again these coastal regions with high cloud droplet number concentration of around 300. And as you move offshore, especially in the tropics, the cloud droplet number concentration can be as low as 20. At least from a satellite point of view. This is taken from the MODIS sensor. So this higher concentration near the continents, if you see what's happening here in terms of radiative forcing of clouds, there is a clear spatial correlation between the cooling of the clouds and also the presence of cloud droplet number concentration. So the question I'm trying to answer here is how we can put together these two pieces of information to say something about and the role of aerosol on modulating cloud droplet number concentration, and how these changes in cloud droplet number concentration produce perturbations in the reflectivity of clouds and reflectivity at the top of the atmosphere. So this, what I'm showing here is trying to convince you that the assumptions we're using to derive cloud droplet number concentration are not so bad. This is a paper recently under review in atmospheric measurement techniques by Ed Greispert. And what we did in this paper was put together a number of field campaigns, of aircraft field campaigns in boundary layer and over the ocean, in boundary layer, cloud top boundary layer, and regimes over the ocean. So we have here more than 10 field campaigns. Let's ignore for a moment the colors and just focus on the correlation pattern here in between the in-situ and the satellite number of droplets. We see that in general, the correlations are very high. We found correlations greater than 0.9, except for a few field campaigns that we need to investigate further. But in general, this analysis gives us confidence that what we are doing makes sense, and we are getting values that compare well with observations. We have some uncertainties, and most likely these uncertainties are associated with optically thin clouds and with clouds that are too small to be observed at the pixel resolution, which is 1 kilometer. So how do we quantify aerosol-Cloud-Radiation interaction from observations? So what we want to know is how perturbations in want to know the perturbations in albedo due to changes in aerosol. So that can be expressed very simple, in a very simple way, and in terms of two components. The first component is the albedo susceptibility, or the ability of the cloud to modify its albedo due to changes in cloud microphysics, and then the aerosol-cloud interaction component, which is how clouds change the microphysics due to perturbation in the aerosol or aerosol concentration. So I'm going to start first by talking about the albedo susceptibility first, because I think this is the easy part of the problem. So what I'm showing here is satellite data. This is MODIS cloud droplet number concentration. This is albedo at the double atmosphere from Ceres. So the correlation shows, and the different colors shows different population of clouds. Black is clouds that are relatively thin or with liquid water path between 30 and 50. Then we increase the liquid water path from 70 to 90, and the blue samples here show clouds that are very thick or very juicy. So if we control for the amount of water content in the cloud, we start to see the Toomey effect, that cloud droplet number concentration and albedo are very highly correlated, and it does reach a saturation point in a sense that, and when you increase the number of droplets to a certain point, there is not much change in albedo. So most of the albedo change starts between 0 to 300, or I'm sorry, 200 droplets per cc. So the figure below is the same figure as above, but this is in a semi-log scale. So what it really shows, this figure, is that we can extract the relationship between albedo and number of droplets using a simple linear relationship. And the linear relationship here we're going to call susceptibility, or more specifically relative susceptibility, because we are talking in terms of fractional change in number of droplets. And as shown in this figure, we have to account for liquid water path, because the amount of water in the cloud also affects albedo, and you really want to select what is the microphysics relative to what is the macro structure of the cloud. So by binning the data into different liquid water path and ranges, you can get different maps of relative susceptibility. So the ability of cloud of change albedo due to fractional changes in number of droplets. So this is for clouds with liquid water path between 30-50, 50-70, and up to 185-115. So in general, we see an increase of albedo with liquid water path to a certain point. But it's also interesting to notice that there are some regions in which the albedo susceptibility is stronger. Again, over subtropical regions becomes dominant. But interestingly, also part of the Southern Ocean and the mid latitudes have some high values of albedo susceptibility due to changes in number of droplets. So we put together all these maps, assuming and knowing the distribution of liquid water path, and we can derive a global susceptibility map, which is what I'm showing here. Again, we see the dominance of the Eastern Pacific clouds, which is, to me, is quite interesting. But it's also interesting that part of the Eastern China and Japan are highly susceptible to change and their albedo changes in cloud microphysics. Now we can express also this map in terms of energy, in terms of shortwave fluxes. So basically, we do the same, but instead of using albedo, we're using shortwave fluxes. And we are having here the effect of latitude, right? So we start to note again that part of the Southern Ocean becomes less dominant, and the subtropical clouds are really the most susceptible to change its albedo due to cloud microphysics. Now, this could be easily, I mean, in a very simplistic way, put in context by assuming changes in number of droplets. If we assume 1% change in number of droplets, this will yield an increase in albedo at the top of the atmosphere between 0.2 or 0.7 watts per square meter, which is really substantial. It's even though this calculation cannot be comparable to derivative forcing of the IPCC reports, we are talking about similar magnitudes here. So this is something that we have to take into account. And of course, we also have a seasonal cycle, and depending on the location of the sun and the latitude, we can have enhancement of albedo susceptibility, especially in the Southern Ocean during the austral and the Southern Hemisphere summer. And we also see, for instance, for the Northeast Pacific, a maximum in susceptibility in summer, which also coincides with the period with that we know that the stratocumulus clouds over these regions are more developed. So, okay, so we have some understanding and just using satellites of how clouds behave due to in terms of radiation due to changes in cloud droplet number concentration. So I'm going to focus my attention now to the aerosol cloud component, which is the most difficult part of the problem. So we want to, in a way, want to estimate changes in microphysics due to changes in aerosol. So from many field campaigns, and here I'm just showing a few, we know that there is a clear correlation between aerosol concentration or cloud drop or cloud concentration nuclei, cloud CCN concentration and cloud droplet number concentration. So this is from DICOM's 2 field campaign. This is from CSET, and this from Activate, which is a current field campaign off the coast of Virginia, the eastern US. This is for San Francisco and Hawaii, and this is for I think DICOM 2 was the region of DICOM was in the Northeast Pacific, but in the southern part of California. So from in situ data, we observe these correlations. So what happened if we try to use satellite data to do the same analysis, trying to correlate aerosol properties with cloud droplet number concentration? The problem is more difficult, and the main issue here is that the only data from satellites that we can use to relate to aerosol is the so-called aerosol optical depth. So the problem with aerosol optical depth is that it's a vertically integrated quantity, so basically measures the optical properties from the surface to the top of the atmosphere. So we cannot really separate in layers, especially the layer that's closer to the cloud. So that's a big issue. So this figure here shows a very informative paper by Andre in 2009, and they show a correlation between cloud condensation nuclei or aerosol concentration and aerosol optical depth from a number of ground-based sites. So if we see this scatter plot, yeah, we can say that there is a very high correlation. The correlation is higher than 0.9. So you will say, okay, this is victory, and it appears that we really can use aerosol optical depth as a proxy for CCN. But the problem is that if you see the range of values here, we are talking about CCN concentration between 10 and up to 10,000, and aerosol optical depth from 0.01 up to 1. So we're talking about a very broad range of values. But if we focus on less polluted environments, which are typical over the ocean, we see that the relationship is, the relationship is poorly characterized. Moreover, if we take a look at the Calypso data, which is what we did here in a 2019 paper, we tried to quantify the fraction of aerosol optical depth contributed by the boundary layer. These are for two semesters. We see that, especially in the tropics and part of the mid-latitudes, the boundary layer aerosol contribute to less than half to the total aerosol optical depth, especially over this region. The Southeast Atlantic is less than 20% of the aerosol contributed to the total aerosol optical depth. However, it's interesting again that the Southern Ocean, it appears that most of the aerosol are concentrated in the boundary layer. And again, every time we talk about the Southern Ocean, we're talking about some very fascinating features. And we definitely, this is the next frontier for climate research. So these profiles here show aerosol extinction profiles from Calypso in the subtropics over the ocean. And all of these profiles have a similar aerosol optical depth of around 0.1. So what we did here was to put together aerosol optical depth, profiles that were close to clouds with different heights. So the black aerosol profile is for lights, for aerosol in the vicinity of clouds that are very shallow, with clouds with heights less than 1 kilometer. The red line is for aerosol clouds in the vicinity of clouds with heights between 1 and 0.6 kilometer, 1 and 1.6 kilometer, and so on. So what we see here is that even though all these profiles have a very similar aerosol optical depths, the vertical profiles are quite different. So one could argue that, or hypothesize that taking into account the vertical structure of clouds matters, because what we really want to, the information that we really want to extract is the aerosol information that's near the cloud in a vertical sense, rather than the entire atmospheric column. So to take a look at the problem, we're going to use the vertically resolved aerosol extinction coefficient from Calypso instead of using aerosol optical depth. So this simple figure shows what we are going to do. We're going to detect the height of the cloud, and in the vicinity of these clouds, we're going to get the aerosol properties in a 300-meter layer. So a limitation of this study is the limitation of many satellite studies that by design, you cannot retrieve aerosol and cloud for the same pixel, because for retrieving cloud, you need cloudy pixel, and for retrieving the entire column of aerosol, you need to derive these properties in cloud-free pixels. So we have to do a game of combining pixels that are close to each other. So we combine 9 months of data over the subtropics and mid-latitudes, and we compare the aerosol properties right below clouds with the aerosol optical depth. So aerosol optical depth is the aerosol property of the entire atmospheric column. And we first notice that the relationship is highly non-linear. But if we focus on one quadrant, which is the more polluted quadrant with aerosol optical depth higher than 0.1 and extinction greater than 0.1, we see that the correlation between aerosol optical depth and extinction is relatively high. But the problem, again, is the pristine environments. If we focus on this quadrant, we see that the relationship first is very scattered, and the correlation is less than 0.3. So again, this analysis is showing us that the use of aerosol optical depth is well justified for polluted environments, but for many areas over the ocean, that's not the case. So now let's take a look at the spatial distribution of a number of cloud and aerosol properties. So the figure on the left is what I've shown before, and cloud droplet number concentration from MODIS. And on the right is aerosol optical depth. So this will be the standard way to relate aerosol and clouds by using these two maps, right? And what we see here is first that for aerosol optical depth, there are two regions that dominate the scene, which is the Eastern Atlantic, the biomass burning region, and the dust region here of the Northeast Atlantic. So now if we do the same map for aerosol extinction coefficient, we start to see an improvement in the correlation. First, the Eastern Pacific starts to be more apparent here. So we see a peaking in aerosol extinction coefficient in the Eastern Pacific, and we see the same for cloud droplet number concentration. We also see the TAN, or cloud droplet number concentration, over the Southeast Pacific to extend farther south, which is also consistent. And the overall spatial correlation between cloud droplet number concentration and extinction goes to 0.64, up to 0.64. In contrast, the correlation between AOD and number of droplets is only 0.4. So there is some improvement. But there is still some regions here, especially in the Eastern Pacific, Northeast Pacific, that doesn't correlate well between aerosol extinction and MODIS, cloud droplet number concentration, and also over the Arabian Sea too. But this is relatively easy to explain by using Calypso data. And this figure shows frequency of occurrence of dust samples according to Calypso, and we see the part of the tropical Atlantic and the Arabian Sea, and even the Mediterranean Sea, that are dominated by dust. And we know that first, we know that dust are not very good CCN, but also we know that these are very large particles. So these large particles are really affecting the way we relate aerosol extinction coefficient to aerosol concentration. So another question that I haven't addressed yet is whether we can use aerosol extinction coefficient as a proxy for aerosol concentration. And because we are only using satellite data, I have to say yes. I mean, we have to do something with the satellite data. We have to come up with a solution. So, but the question, it should be reformulated and in a way that we need to ask ourselves how we can use the aerosol extinction coefficient data in a way that looks more similar to aerosol concentration. So we have to take into account a number of factors. One of those factors is relative humidity. You know that depending on the type of aerosol, and this aerosol can grow just because of the humidity. It's a swelling effect of the aerosol, depending on the hygroscopicity of this aerosol. And and we are going to see this effect from satellites. And this is the example of this is in this figure. This is a time series from a ship-based field campaign off the coast of California. So this is a time series of, let's say, aerosol extinction coefficient. It's really scattering, but it's very close to aerosol extinction coefficient. So the green line, they are ambient humidity measurements. Okay, the black line is measurement from a sensor that sample aerosol concentration, dry aerosol concentration. So I took these samples and I use Means theory to calculate the theoretical aerosol extinction coefficient of dry aerosol, which is the black line. And then using in situ data, I came up with a humidification factor correction, which is a function of relative humidity. And we were able to take the ambient humidity observations and convert them into dry aerosol extinction coefficient. So this is possible to do using empirical relationships, but also using analytical and theoretical considerations and knowing the aerosol type, some basic information about the refractive index, etc. So if we're able to somehow correct the ambient humidity measurements and derive dry extinction coefficient, we can actually correlate aerosol extinction coefficient with aerosol concentration, or CCN, which is what I'm showing here. We found a very high correlation between these two. And this is also possible when we apply correction factors for accounting for the relative humidity of this aerosol. So what I want to show now during my last 5 or 10 minutes is talk a little bit about the satellite data record, whether we can observe the Toomey effect in the satellite data record. And I know that many people are very skeptical about this because we only have 20 years of reliable data from Aqua and Terra. So we only have 20 years of data. But we think that even if we're looking at 20 years of data, this could be very informative. So what we did was taking Aqua data from 2002 until 2019, and we see trends. We try to compute trends of cloud droplet number concentration, which is what I'm showing here. And this is material of a paper in preparation. And this is cloud droplet number concentration for the period of 2002 and 2019. The blue colors is a negative trend in cloud droplet number concentration, meaning that number of droplets has decreased in time, and the red and orange is increasing number of droplets. And the crosses indicate regions in which the slope is statistically significant based on a couple of statistical tests. So what it's interesting here is first the Northern Hemisphere, part of the continental US and the Gulf Stream, in which there is a dramatic decrease in number of droplets. The same thing for parts of Europe. And it's more difficult to interpret this cloud here over the African part of Argentina, mainly because you don't have too many bandolier clouds here. And if we look at the satellite record, but in this case, rather than looking at the satellite record, I look at the MERA 2 aerosol optical depth. And I know many of you are saying, okay, you have been talking about how terrible is aerosol optical depth, how you can use aerosol optical depth to look at trends. And in a way, that's right. I mean, I'm still arguing that many of these analyses, past satellite analysis, need to be revised because aerosol optical depth isn't a good proxy. But we're talking here about trends, and most likely trends in aerosol optical depth are also followed by trends in aerosol concentration. And what we are showing here, it's a MERA2 reanalysis of total aerosol optical depth. And this the lower figure is for sulfate aerosol optical depth. So we see that during the past 20 years has been a decrease in aerosol optical depths and sulfate aerosol optical depth, particularly over part of the continental US and the northwestern Atlantic, which is consistent with what we're seeing here. So we're finding some evidence that there might be, I'm going to say might, the word might very carefully, there might be some sort of tuning effect during the past 20 years due to a decrease of aerosol due to the better environmental and laws in part of the US and Europe. And of course, it's also relevant to look at the meteorology and trends in other properties, cloud properties. And in this case, I'm showing in low cloud fraction and trends. And what we see here is that there has been a decrease in cloud fraction over the Eastern Pacific. And I believe this is related to El Niño, La Niña events. And it's definitely a topic for a different presentation. But what is interesting is that for the region of interest, mostly continental US and the adjacent ocean and part of Europe, there is no clear trend here. So it appears that even though we don't have the final evidence that this is real, and we are not very highly confident that the relationship between aerosol and cloud, this changing trend is associated with the change in aerosol optical depth over this region. And we have, and the analysis we have, preliminary analysis is that this is likely, it's possible, but definitely more work needs to be done. So during this presentation, I have shown, I tried to convince you that there is space, we can still do more progress using satellite data. There are smart ways to use satellite data, exploiting the resolution, pixel resolution, and understanding the assumptions that we need to make to estimate cloud droplet concentration, and some progress can be done. And I'm particularly it's very clear to me that many of, if not most of the satellite assessment needs to be revised by looking at the vertical structure of the aerosol. And there are many challenges ahead. And one of the challenges that it's difficult to address with satellite data is the size problem. And shallow cumulus clouds are very difficult to observe with satellites, mostly because we are talking about clouds with sizes more than 200 meters, which you cannot observe and with great accuracy from satellites, but also because we don't have a comprehensive description of the chemical and optical properties of the aerosol. And also, I haven't talked about precipitation, and this is also something that we need to take into account. And it definitely is going to be addressed in a future talk if they allow me to. Another point that I want to make here is that in-situ observations are still replaceable. We need in-situ observations as ground truth to validate our satellite data. And I would like to conclude this presentation by talking about what is the future of the satellite observations. So during this past 30, 40 minutes, I talk about the A-train satellites and the sensors. So the bad news is that many of these sensors are approaching the end of their operational life. And moreover, Calypso and CloudSat, these sensors might die any moment. It could be in 5 minutes, in a month, 2 months, in a week. So it's very uncertain. So we cannot count on Calypso and CloudSat for more than a year, most likely. The good news is that series program has deployed a number of sensors. So the continuity of the climate data record is guaranteed for the next 10 years at least, because we have at least a couple of satellites, swarming PP, NOAA 20, that have the series instruments too. So what's going to happen in the future? Well, there may be a few years that we're not going to have radar and LiDAR data. But NASA, in anticipation to this issue, NASA put together a group of scientists and researchers that helped design the next suite of atmospheric observation and the next generation of satellite constellation, which is the so-called atmospheric observing system. So during this past couple of years, a number of scientists have been working with NASA to come up with the design. And recently, NASA selected this architecture for the new generation of the so-called A-train. It's not really an A-train, but the next generation of constellation. So this is formed by 3 satellites, 1 polar orbiting satellite and 2 inclined satellites. So the polar orbiter has a K and W band Doppler radar that will allow derivation of precipitation and vertical motions, a microwave radiometer for cloud properties and also ice properties, a more advanced LiDAR, a LiDAR that's more advanced than Calypso, the high spectral resolution LiDAR, and also polarimeter that will be central for better characterizing the optical properties of this aerosol. And the 2 inclined satellites will also include Doppler radar and a simpler LiDAR, which is similar to Calypso. And the main advantage of these inclined orbit satellites is that they will be able to resolve the Diurnal cycle of aerosol and cloud property. And I'm sorry about that, that's my cat. And what is fascinating about this is that they're expecting to launch these first 2 satellites as early as 2017 or 2019. So I think there is a message of hope here for the scientific community that things are going to be revolutionary in 5 or 7 years more. And I would like to conclude here by advertising our NASA postdoctoral program. We're looking for good students, good postdocs to join our group. We're looking for people able to work in the radiative transfer field, algorithm validation, algorithm development and validation studies, but also researchers that their research interest is related to the topic of this presentation, aerosol-Cloud-Radiation interaction. Also, we are including hyperspectral remote sensing in our group, and with the goal of deriving profiles of temperature and humidity. So if you're interested in any of these topics and you want to apply for the program, just contact me or Billy Smith, and we'll be happy to answer a question. And if you're interested, we can help you move your project forward. And that's all I have to show. Thanks for your time.
Thank you, David. That was a very engaging, clear presentation. Great figures. So thanks so much. So I'm wondering if there's any questions out there. We should start with the students at Rasmus and then expand it to the larger audience. I know I have some, but I'd like to wait. I see one in chat. Do you see it? I'm happy to read it out.
Yeah, okay. I'm reading it now. Yeah, that's a good question. It's about, and the question is about climate models and whether they are over predicting and the aerosol-Cloud interaction and Toomey effect. So that's a very good question, because if you do a literature review and you see this assessment compared with satellite data, they do show that climate models tends to predict a stronger aerosol interaction. But I'm a little bit hesitant to actually say that the models are over predicting this effect, because I'm not fully confident that, for instance, by using aerosol optical depth as an aerosol proxy, you are going to get the best estimate of aerosol cloud interaction. So my argument here is that if you are using aerosol optical depth and you're not very careful at subsampling your data and applying the proper filters, you are going to get a very noisy signal from the satellites. So if you're getting a noisy signal, most likely you could, I'm just hypothesizing this. So you're getting a noisy signal, you are not going to be able to fully see the extent of the aerosol cloud interaction effect. So then you're comparing noisy results. You're trying to validate your climate models with noisy results. So it's a good question, and I think it's really an open question.
Thank you very much.
Anyone else? I have a question on the using the LiDAR-derived subcloud extinction for ACI, which is, obviously good idea. I didn't see you talk about aerosol typing in that, and I know it's done with the CalIOP data. So I'm wondering if what your thoughts on that, or what where.
Yeah, that's a good point, and I just briefly mentioned the effect of dust, right? So dust in particular is something that Calypso classifies very well, extremely well. So, and we know that dust is not an ideal CCN. So, and at the same time, they are very complex geometrical structure, and they're very large particles too. So that also it's going to affect the way you interpret aerosol extinction coefficient. So getting back to your point, yeah, it's important to do this analysis for different aerosol types, right? So perhaps the easiest way to do this is, easy way to do this is by staying away from the continents, because you know that away from the continents, the mixture of aerosol is not that complicated. But yeah, in principle, you can use aerosol typing information from Calypso to do the same analysis in terms of the different 7 or 8 aerosol types. Yeah, that's a good point, and it could be also relevant because different aerosol types have their ability of swelling due to changes in humidity is different depending on the type of aerosol. But then there is another question, whether you can trust the aerosol typing from Calypso. So that's a topic of a different presentation. In a way, yes, you can trust it, but to some limits. There are limits too. Yeah.
Yeah, the dust over the northern tropical Atlantic is often mixed with smoke in the winter, and smoke is an excellent CCN. So yeah, it could be interesting to see how well CalIOP does.
Yeah, it's true. It's CalIOP. Yeah, in principle, you can get mixed dust and smoke from CalIOP. It's what they call polluted dust. It's an aerosol type from CalIOP or CalIOP. So it might be possible to get some information about that mixture from Calypso. Yeah, that's an interesting point. Yeah.
Are there any other questions from the larger audience? I could certainly keep going, but I don't want to dominate.
I have one.
Great. Hey, Graham.
Hi, David. How are you? Yeah.
Very good. Very good.
Yeah, David, I wondered if you could give us some thoughts on challenges of looking at cloud fraction responses to changes in aerosol from satellites.
Yeah, this is really an excellent question and a difficult one too. We know, okay, so it depends on what you want to do, right? So if your interest is looking at trying to find a link between aerosol variability and changes in cloud fraction, that's a difficult thing to do. And it's very difficult for the reason that if you are retrieving aerosol and you're getting closer to the cloud, the scattering property of the aerosol changes, and you're going to see a spike in the energy reflected by this aerosol, just because they are bigger. And eventually, what you are going to see is an increase in aerosol optical depth. This is just a consequence of the aerosol swelling near the vicinity of clouds. And then you have a second effect, which is a 3D transfer effect. That because you are near the edge of the cloud, you have some horizontal photons. So those two things are going to create an artificial correlation between aerosol properties, namely aerosol optical depth and cloud fraction. So that's difficult to do. You can, to some extent, remediate that effect by using Calypso. You are going to remove the 3D effect component of that problem. Now, if you really want to find correlation between cloud fraction and aerosol, it has to be very carefully designed, the analysis, in a way that the aerosol you're trying to sample that not that close to the clouds. And I think Thomas Barnay and Sasha Marshak, they have a paper on that. So they give a number of recommendations on how to do this, how away you have to be from the cloud to get aerosol properties that are not that affected by aerosol. But blindly using, for instance, MODIS, aerosol optical depth and MODIS cloud fraction to do this, I will say that it's going to give you a huge overestimate of the aerosol cloud effect, the effect of aerosol on cloud coverage. Yeah. If you want to, if people really want to use, still want to use MODIS, they have to look at the pixel level data. So you have to play with the 1 kilometer data and start playing, looking at the vicinity of clouds and doing a careful filtering. But it's very often that for climate modeling, climate model assessments, people use 1 degree or level 3 data. And I would not recommend that. I would not, frankly, I will not trust those analyses. Yeah. But it's a good question. It's a difficult one too. Yeah. Thanks.
All right, we're on the hour. I do have one more question, but people should feel free to, take off and go have lunch in Miami. And thank you for attending Compass. And thanks again to our speaker. But stay on the line, David.
Thanks, Magida. Yeah, sure.